I'm just sorry about the noises. I couldn't find, I'm just in the public, so I couldn't find any quiet place. I'm sorry if there are some noises in there.
It's okay, no worries.
Okay, perfect. Thanks everyone for joining my presentation session. My name is Sarvenaz, and our paper is about addressing class imbalance in facial emotion recognition. First I will go through the introduction and the problem statement, and then I will introduce you the concept of face recognition and emotion recognition respectively. After that, I will go through a brief introduction about CNN or convolution neural network and two popular CNN architectures. Continuously, I will explain the dataset preparation for this work, and then I will propose a SMOTETomek technique, which is the main part of the paper to address the issue of class imbalance. And then after all, I will provide the result for both the initial and modified data set. And finally, I will wrap up with a conclusion. So since the human face plays an integral part in expressing a person's mental state, facial expression analysis is a significant research focus with numerous potential uses. While it may come easy for most humans to process emotions without any extra effort, computers have struggled with the idea of recognizing them automatically for decades. Specifically, we study the task of facial emotion recognition based on two deep learning models using our suggested dataset. We use various face images for 7 emotions, which are happiness, anger, sadness, fear, neutral, disgust, and surprise, and propose how to improve the accuracy of emotion detection. The first contribution of this work is a comprehensive analysis of popular emotion recognition datasets. We also describe how images are categorized in each dataset. The second contribution is creating a custom dataset consisting of the 3 dataset or 3 different sets of images that we use to cover a wide range of variations in face images. And the last contribution is improving class imbalance problem in our custom emotion recognition dataset over VGG16 and ResNet50 networks. And at the end, I will show how SMOTETomek technique improves the distinction accuracy over VGG16 and ResNet50 networks. So face recognition. The challenge of recognizing and validating people in an image by their face is known as face recognition. It is sometimes defined as a 4-step process that begins with face detection, then moves on to face alignment, feature extraction, and ultimately face identification. Face detection is the challenge of identifying and localizing one or more faces in a picture in computer vision. Face alignment is a method using computer vision to identify the shape of a face in a digital picture. For the feature extraction, I can say if the data is too large to analyze and is suspected to be redundant, there is a method called feature extraction to be used, and it's a reduced representation of the input data that only contains the essential information from the input data. And at last, face recognition, which is defined as the job of identifying a face in a picture or video against a pre-existing database of faces. So let's talk about some of the common face recognition challenges. Illumination, which usually refers to light fluctuations, pose that pose changes are usually sensitive to facial recognition system. So for example, when a person's head moves and their viewing angle changes, the posture of their face changes. And as a result of the head motion and differing camera angles, intraclass variances in face appearance result in reduced face recognition rates. Occlusion, and which you can see it in the third figure, is usually referred to a blocking of one or more portions of the face. And low resolution is another challenge, which usually refers to the pixel to the images that usually have a resolution of less than 16 by 16 pixels. So let's talk about emotion and emotion recognition. Emotion is related to mental states, thoughts, feelings, behavioral responses, and levels of happiness or dissatisfaction caused by neurophysiological changes. The technique of recognizing human emotion is called as emotion recognition. And 7 emotions that we use in this work is our happiness, sadness, fear, disgust, anger, and surprise. So convolutional neural network, or in short CNN. As the name implies, a neural network is a collection of algorithms that tries to discover hidden connections in data by mimicking how the human brain works. And the features are extracted in this layer. The convolution layer extracts features using a combination of linear and nonlinear processes. This layer is usually applied to its input to generate the output, which is called a feature map. Pooling layer performs a standard downsampling operation on the feature maps, reducing their dimensionality to prevent the system runs out of memory. The result is a single value for each square segment of the feature map. And the most 2 common types of pooling layers are max pooling and average pooling. Fully connected layer is usually the last layer in CNN networks, or let's say convolutional neural networks. And the goal of this layer is to convert a pooled featured map from a 2-dimensional structure to a one-dimension array of integers. This means that the final convolution or pooling layer's output are flattened, and the output is the probability for each class in a classification task. 2 popular CNN architectures are Residual network, or ResNet, and the other one is VGG16. Let's talk about the ResNet first. Usually a greater error rate in the task of classification happens when the number of layers increases. This is because as the number of layers grow, a typical problem in deep learning called vanishing gradient emerges. This issue changes the gradient value to either 0 or too large, which prevents the system to learn. So as a result, the concept of residual network was introduced, which works with a smaller number of layers compared with other CNN architectures, and resolves the vanishing gradient problem by adding the input features to the output. VGG is another network architecture, which is shown in the second figure. So rather than having a large number of parameters, VGG16 employs 3x3 convolution filter layers with a stride of size 1. And at the end of its architecture, it has 2 fully connected layers that are shown in blue. And also the output is then followed by a softmax function. So the total probability of each class sums to 1. Unfortunately, there are two major drawbacks with VGG network. First of all, it is its speed is very slow in training. And the second one is that the network architecture weights are quite large themselves. So it prevents the system to learn efficiently. In this slide, I will introduce 3 datasets I use to create my augmented dataset. The first one is EMOTIC, or emotion in context, which is a dataset of images with people in a real environment. The second one is KDEF, or Caroline Scott directed emotional faces, which is one of the most widely used human facial expression databases. And the last one is CK+, in which the facial behavior of 210 adults was recorded, and participants were instructed by an experimenter to perform a series of 23 different facial displays. As I said, the dataset used in this work is a combination of 3 different datasets, CK+, EMOTIC, and KDEF. Firstly, the augmented dataset is trained on a deep neural network called FaceNet to extract features from images of a person's face and detect the face. Using FaceNet, which is an embedded face recognition and clustering network, is a recommended approach to detect faces. It learns a mapping from photographs of faces to a compact Euclidean space in which distances directly correlate with measures of face similarity. Using this algorithm allows us to extract high quality characteristics from faces. The model is itself a triplet loss function trained deep convolutional neural network that promotes vectors for the same identity to grow more similar images. After the face images are detected, they should be augmented by image transformation to be fed to the input of emotion recognition networks. The final dataset consists of cropped, rotated, and horizontally flipped images of the original dataset. After the faces are detected, the new dataset is split to training and testing. So our training dataset was 70%, and then our testing dataset was 30% of the total number of the total dataset. And eventually the split dataset is trained on VGG16 and ResNet 50 networks. After splitting the total images into training and testing, the distribution of 7 emotions is shown in this table. And as you can see, high variance is shown in the number of images in each class in both training and testing. This ultimately degrade the performance of the model. So here's the VGG output result. As shown in the second figure, the training accuracy is 52.31%, and testing accuracy reaches 52.49% after 30 epochs. Through training our dataset on VGG16, the following confusion matrix has been obtained on the top right of the screen, and labels are shown from 0 to 6, which maps to anger, disgust, neutrality, sadness, and surprise, and then fear and happiness, respectively. The blocks located on the diameter of the matrix show how well each class is distinguished. And happiness, as you can see, or label 6, is the only emotion that reaches high accuracy of determination, while other emotions reach very low accuracy. Here is the ResNet output result. After 30 epochs, the training accuracy reaches 58.39%, and the testing accuracy reaches 55.63%. Through training our dataset on ResNet 50 network, the following confusion matrix has been obtained. Again, similar to VGG, happiness is the only emotion that reaches high accuracy of determination, while other emotions reach very low accuracy. As you can see, these networks seem to be incapable of detecting other 6 emotions in the task of face emotion recognition with the VGG16 and ResNet50 networks. They also show high off-diagonal values, which is due to class imbalance. And in simpler words, the number of examples in the majority class dominates the number of samples in the minority class, and the model is unable to learn from minority class though. So there are 2 approaches to tackle this problem. One approach is to duplicate the images in the minor class, and the other approach is to undersample the majority class. The first one is the approach used in this work is to overcome is a combination of both oversampling and undersampling to overcome the imbalanced data. So let me give you a brief introduction about each approach. SMOTE or synthetic minority oversampling technique is an approach to oversample the minority class, and this can simply be done by duplicating examples of minority class. However, this method doesn't provide any additional helpful information about the data. To defeat this, a method called SMOTE is used. Tomek link is another approach to solve the problem of imbalanced data, which refers to undersampling the majority class, and this can be done by removing random samples from dataset. However, some information is deleted and is missed. So to defeat this, a method called Tomek link is used. And it is this approach is done by using nearest neighbor rule, or NNR in short. And SMOTETomek, which is the technique we used in this paper, is a combination of SMOTE and Tomek link approaches. In other words, it has the ability to oversample by creating synthetic data for minority class, as well as the ability to undersample by removing data from the majority class. And more accurate results were obtained by using SMOTETomek for the task of data augmentation. As you can see, the distinction of emotion recognition got better after using this approach, and as it is observed, the blocks on the diameter are darker, which means the classes are classified more accurate when the number of samples in each class is balanced. Same thing with ResNet50 network. The system learns emotion detection better by using I'm just getting a message on my can you guys still hear me? I think so. Yeah, it's all good. Sorry about that. Yeah, as I said, same with the ResNet50 network. The system could learn better the task of emotion detection by using the SMOTETomek technique, and it's also shown in the confusion matrix on this slide. And the darker colors are dedicated to different blocks of emotion categories, as you might know. This confirms the effectiveness of the proposed method compared with the initial one, and also comparing the enhanced confusion matrices with the initial matrices, more consistency on 7 emotion categories is resulted. So for better comparison, we have shown how VGG16 and ResNet50 improvement in these 2 figures. The y-axis shows the accuracy of the architecture over a certain emotion category. The x-axis represents the emotions. The enhanced dataset, which are shown in color green, gives priorities to the emotion categories with less data. For example, label 4 or sadness emotion has a small number of images. It only contains 327 images, and it shows more accuracy in the figure compared with happiness emotion, which has 1,514 images. This improves the accuracy up to 61.16% in VGG16 and 60.71% in Resident 50 for certain categories. So thank you so much for attending my presentation. I'll be happy to answer any question.